postdoc at the University of Florida, working with Andrea Lucky, and today I will be presenting the work that's led by the PhD student in our lab, Jason Williams, in collaboration with the Ant Lab at the Smithsonian and Towson University. The title of my presentation is Global Domination by Crazy Ants. Now, for those of you that are not familiar with ants, you're probably asking, what are crazy ants and what makes them crazy? Well, so these are what crazy ants look like. They're called crazy ants because if you disturb them, they start running around in this really erratic pattern that seems crazy. Sorry, it's not more exciting than that. But they are Formicides in the genus Nylanderia, and they are quite abundant in terms of diversity, species richness, and abundance. There are more than 130 described species worldwide, and many more undescribed. And they're often one of the most commonly sampled ants when you go out and do any sort of leaf litter sifting or something. But despite this diversity, they have very limited morphological variation. So from these pictures, there are two different species, and there are many more that generally have this look of they're pretty hairy, they're a little squishy looking compared to some of the more heavily armored ants. So for people that's not familiar with this group, it's really difficult to identify these. But to make matters worse, there are more than a dozen of these species in this genus that's been found worldwide as exotics. So this is definitely problematic. They start showing up in different places, likely due to human trade routes, and we can't really identify them. And the picture on the bottom is the tawny crazy ant. You might have heard of these. They're basically around the Gulf Coast of the southeastern U.S., and they're just one of these many exotic species, and these often fall into these species complexes, right? So I'm showing you these species pairs top to bottom. Now, from these pictures, they might look pretty easily distinguishable, but once you have a large enough sample, a lot of these characteristics starts to break down, so making identification really difficult. And both morphological and Sanger era sequencing have tried, and we don't have satisfactory answers on how to accurately identify these things. So, at this conference, we've heard a lot about different types of hybrid enrichment. Alex just presented one on anchor hybrid enrichment. The other popular, the one that's gaining a lot of popularity is the enrichment of ultra-conserved elements, or UCEs. It's been widely used in phylogenomics since its introduction in the early 2012, I think. And because we can use it for deep and shallow level evolutionary studies across the diverse groups of organisms. And we can also use museum and degraded specimens, which is great, as a lot of these species. They're found worldwide, but often there aren't that many specimens, so they have older museum specimens that we can use. So UCs have been adopted in ant phylogenomics as well. So here's a study of the subfamily Formicidae by Blamer et al. And they actually sequenced a few of these Nylanderia. I should say that this genus has also been controversial in its placement. It's been moved in and out of other groups. So using UCEs, that they were able to show that Nylanderia is monophyletic. But you see that the taxon sampling is really limited because they were looking at the entire subfamily and only included 4 individuals within Nylanderia. So our goal, because of all these problems with this group and the economic importance, we are interested in building a large-scale UCE phylogeny of this genus. And what we are interested in investigating the age and origins of this genus as it's found around the world, and also determine the number of origins for these exotic species. So for the molecular method, we used UCEs, like I said before. We took a total of 112 samples around the globe, and this includes 92 samples within Nylanderia. This is about 38 species, depending on who you ask when it comes to these species complex. And we also included 20 specimens from outgroups from various other genera. Like I said, it belongs into this species group, so we just want to make sure, what we're calling currently as Nylanderia actually falls within Nylanderia. And the workflow largely follows this diagram on the right. So this is actually a review paper that I did on some like the best practice for UC analyses focusing on arthropod phylogenomics. Hopefully this will be out soon. But in short, we used a Hymenoptera version 2 probe set, which targets more than 2,000 loci, UCE loci, and we process the data using Phylogenomics. So here is the phylogeny. I know being like you can't read anything. This is typical of any phylogenetic talk. So this is maximum likelihood tree generated using IQ tree, and we used we also played with the data completeness like from 50 all the way up to 95, and we ended up settling for a 75% complete matrix, meaning that for each of the locus included in here, you have to be present for at least 75% of these 112 taxa. So this filters down the data down to 787 loci. And we partitioned this data set using the sliding window site characteristics based on site entropies. So this is a newly developed models to partition UCE data as the ultra-conserved core region evolves at a very different rate than the flanking region, which is what we're interested in, the much more variable areas. So this tree, I'm showing you the cladogram is on the left and the phylogram is on the right, showing the branch length. You see the branch lengths are all pretty short. And then the supports that we're showing you here is the SH-AORT that Alex talked about earlier, but also the ultra-fast bootstrap. So they're just two different types of support. The main takeaway here is that Nylanderia, of course, it recovers monophyletic, which is great. Otherwise, this will be a lot more problematic. But also, there are multiple origins of these exotic species, right? So it seems that this group, rather than just being a specific trampy clade that everywhere you move to become an exotic, it is a genus-wide phenomenon. So likely, if more of these species were accidentally transported to other places, they might be able to establish themselves as well. I also have the clades mapped with the different biogeographic locations. I'll come back to this in a bit. But we also looked at the concordance factors. So if you're at the main talk yesterday about concordance factors, it's an alternative way of measuring support rather than the traditional bootstrap. So we use the GCF as a gene concordance factor, right, defined by the percentage of gene trees supporting a branch, or this newly developed site concordance factor is the percentage of decisive sites in an alignment that supports a branch. So when we plot these two against each other, we have the GCF on the x-axis, the SCF on the y-axis, and then the bootstrap value is color-coded there. You see the bootstrap maxed out pretty quickly here, right? So it hit 100% pretty quickly, but this shows you an interesting pattern, low GCF versus high SCF. And yesterday, Wang said that anything below 33%, when it comes to SCF, you shouldn't trust that. I had like a moment of panic. I was like, oh crap, I had a few that were below. So yesterday I checked on these. So there are 3 nodes here that's below 25%, and those are all just within the species complex. So they could be just conspecifics or very closely related ones. So I was a little worried that was fine. But what does this mean, right? So this type of pattern, low gene concordance factor versus high site concordance factor, it could be due to the short branch length that I showed you earlier, or it could be either incomplete lineage sorting, or more likely, probably just due to stochastic error. Right? So this is an interesting measure to look at the data that you would not otherwise see using the traditional bootstraps. Oh, I should say this was built using the IQ tree 1.7 beta. So it's not officially out yet, but the preprints out, and the tutorial is very simple. So we also did dating on biogeography with divergence dating using a reduced data set to increase the computational time. So we used a 90% complete matrix of 65 taxa and 45 genes, and we used 4 fossils, 2 of which are in Nylanderia and 2 stem fossils that's outside of this. And we used a fossilized birth death model, and for biogeography, we did biogeographics using a deck model. So here is the time the data tree. The topology, again, is pretty similar to the other one, just with less taxa, but what I want you to draw your attention from it is this genus seems to have originated from Indo-Malayan around 32 million years ago, so an Asian origin, and then have since then diversified rather rapidly across the world, hence the title global domination. So we have 4 different clades in Nearctic, Australasian, Afrotropical, and Neotropical. And these 4 clades ranges from late Oligocene to mid-Miocene. And curiously, this group is not found in Europe, except for one of the fossils that's in Europe. So for some reason, they could be either there and they become extinct, but it's just an interesting pattern that they're found everywhere else except Europe. And another thing of interest here is that you see that the Americas have been invaded twice, essentially, right? Because the Nearctic is rather distantly related from the Neotropical, so that's something interesting that we're looking into. So just to conclude, Nylanderia itself is monophyletic and it originated in the Malayan around mid-Eocene. And since then have diverged into 4 major biogeographic clades that range from late Oligocene to mid-Miocene. And then there are 2 separate introductions into the Americas from Indo-Malaya. And finally, there are at least 5 origins of exotic species that's currently present throughout this group. And there are likely more. As we're increasing the taxon sampling, focusing on South American and Caribbean groups, as these are particular species rich with a lot of undescribed species. So here's a picture of Jason, the lead author at the Smithsonian. He's actually there right now, probably doing exactly this to prepare for more UC libraries. And we're hoping to resolve some of these species complexes with additional sampling. Okay, with that, I'd just like to thank my lab mates, the Lucky Lab, all these different individuals that have given me help for the analysis. All these museums and enthusiasts have donated specimens and various funding sources. I'd be happy to take any questions. Thank you. Oh, sorry, yes.
Why aren't they in Europe?
Well, that's what we're trying to find out, right? So one of the fossils is found in one of the Baltic ambers, right? So they could have existed there and just have become extinct. That seems to be the most likely. I guess we could do some sort of like modeling to see if they're capable of being there. Yeah, so it is interesting. They're not there yet, and they have not been accidentally introduced back into Europe. So, yeah, I don't have a great answer for that. That's what we're trying to figure out.
I'm curious about that partitioning scheme. You used that new method that was introduced by Calculator Polo and here.
Yeah.
I tried using that, but I found that what happened in my data set was I was getting these warnings about numerical instability in that tree, and then when the analysis finished, I noticed that the tree length was extremely inflated. So relative branch lengths didn't really change compared to by locus partitioning, but the total tree length increased by a factor of 10. So I wonder if you were noticing anything weird about it.
No, I tried that at my locus. I didn't really notice difference, but we could talk more.